Hey everyone, welcome back to Code No Evil. In this video, we are going to solve a very interesting dynamic programming problem called burst balloons. Now, this problem is marked hard, and we do need a couple of hints to get to the optimal solution here. Now, we are given n balloons which are indexed from 0 to n minus 1, and each balloon has some number printed on it, and we are asked to burst all the balloons. Now if we burst the ith balloon, we would get the number of coins which is given by this formula, which is nums of I to nums of I minus 1 into nums of I plus 1. Now if we were to go out of bounds, then we have to treat as if there is a balloon with 1 painted on it. Okay, now let's walk through this example. Let's say the first balloon we burst is 1. Now the number of coins that we would get would be the number on the balloon we just bursted, which is 1, into its adjacent balloons, which is 3 and 5, which is given here. 3 into 1 into 5. Now let's move forward. Let's burst 5. Now the number of coins we would get would be 3 into the balloon we just burst, which is 5 into 8. Now let's burst 3. Number of balloons we would get is 1. Because we went out of bounds, we are supposed to treat as if a balloon with 1 printed on it exists here. So we would get 1 into 3 into 8. Now let's move forward. Now we burst 8. Now we would get 1 into 8, and since we again went out of bounds, we are supposed to treat it as 1, which is 1 into 8 into 1, and if you add all these up, we would get 167. Now let's see how we would approach this problem. Let's start with a very brute force solution where we would enumerate all the possibilities. Let's say, what if I burst the first balloon first? What if I were to burst the second guy first? What if I burst the third guy first? Let's see this with an example. I have an array with 1, 2, 3. Now, if I were to burst, let's say, the second balloon first, then my sub problem would be this and this. But as you can see, these two problems are not independent. Now if I were to burst this guy, I would get 1 into whatever is left from the right sub problem. So these two problems are dependent on one another. These are dependent. Now let's reverse our way of thinking. Think of some other approach for it. Now let's say I'll copy the same array here. Now let's say I burst the second balloon last. Now if I'm doing that, I would again have two subproblems, which would be this and this. This is my left subproblem. This is my right subproblem. Now if I burst the second balloon first, I am in on my left subproblem. Now if I burst this guy, the amount of coins I would get would be 1 into whatever is present on the right boundary. Now in this case, since 2 was burst at the last, when I'm on the left subproblem, I for sure know that 2 would exist on its boundary. Now, so the coins that I would get would be 1 into 1 into 2. Now similarly, I'll go to the right subproblem. There the number of coins that I would get once I burst 3 would be 2 into 3 into 1. 2 into 3 into 1. So let me draw the decision tree here briefly. So we are choosing if we want to burst the first balloon the last, the second balloon the last, third balloon the last, or up to k balloons. Now how would my left and right subproblems look like? Let me define it mathematically. So my left problem would be, if I'm bursting the kth balloon, then it would be f of L to k minus 1. Similarly, my R subproblem would be equal to f of k plus 1 to R. Now let's try to define my original problem in terms of my left and right subproblems. So f of L to R, oh sorry, f of L to R would be max of where k is going from L to R would be f of L to k minus 1 plus f of k plus 1 to R plus nums of L minus 1 into nums of k into nums of R plus 1. So we have actually defined our subproblems. So here this is our original problem which we are trying to solve. Original problem, and this one and this one are the left and right subproblems that we have defined previously. So we have successfully expressed our original problem in terms of the left and the right subproblems. Let's start with making the decision tree for our approach. So I'll just write down the same array that we had, 1, 2 and 3. Also name the indices 0, 1, 2. Okay, so now our function would have two states. One would be the start and the end. For this example, the start would be 0, the end would be 2. And let's say we'll start with our decision. Let's say we burst the first balloon last. Okay, now we would get one out of bound state and one state where the parameters would be f of 1 to 2. Now let's say we burst the second balloon last, you would again get two states, f of 0 comma 0 and f of 2 comma 2. Now let's say we burst the third balloon last, you would get one out of bound state and one f of 0 comma 1 state. Now let's go a step deeper. Now if we burst the first balloon from here last, we would get one out of bound state and one f of 2 comma 2 state. Now, as you can see here, we have overlapping subproblems, is this and this. Had we followed this recursive approach, the number of states would have been n to the power n. But we know the number of subarrays for a given array can be only n square. So then by using memorization, we can get down the states to n square. So for getting it to n square, we will be using dp. Yeah, so as you can see, we had written this recurrence relation. Now let's see how can we leverage this to fill our dp table. Now as you can know, you know that we had these left problems and right subproblems that we needed to solve. Now what we are gonna do, since it's a subarray, our subproblems are all subarrays, we would be pre-filling some values by hand. All these values would be pre-filled. Okay. Now if I want this problem to be filled, I would need some subproblems from here and some problems from here. So what we are gonna do, we are gonna diagonally start filling our dp table, and that's how whenever we are on a particular problem, we would have all the problems that we need for this subproblem all pre-computed. Okay, so let's start with the code walkthrough. So here we have a n cross n vector defined. This is our dp vector, and we are pre-filling its value. So basically, essentially, we are filling in the 0, 0th cell, the 1, 1 cell, all having a size of 1. Now then, here we are traversing our dp vector diagonally, and we are computing the left subproblem and the right subproblem. Now, if we reach a subproblem which is not valid, so we then put 0 in that subproblem, and then we are calculating the boundary values as lval and rval. These are also being calculated, and if we are reached an out of bound index, we are marking them as 1 as it was given in the problem statement itself. And finally we are caching it within our dp vector, and this is the recurrence that we had just written down. Now let's see the time and space complexity of our solution. So the time complexity of this solution would be O of n cube. Since our dp vector has n square states and our kth loop would be running for n times, the total time complexity comes out to be n cube. Now the space that our dp vector is occupying is O of n square, since there can be at most n square subarrays for a given array. So this is the time complexity, and the space complexity is O of n square. Thanks a lot for watching this video, guys. If you found this video helpful, don't forget to like, share and subscribe for more content like this. Drop your thoughts or questions in the comments. I would love to hear from you. See you in the next one.